Behind me is an engine undertaking groundbreaking research into hydrogen power for aviation.
Aviation is on the verge of something massive. For decades, jet fuel has been the only option to keep commercial aircraft in the sky. But a series of breakthroughs in late 2024 and early 2025 have suddenly made hydrogen engines not just possible, but inevitable.
I'm very, very interested in hydrogen engines for aircrafts because I think the limiting factor here, as I understand it, has been carrying hydrogen as a fuel on the aircraft.
Major manufacturers are moving past testing phases and signing real contracts. The timeline for when you might board a hydrogen-powered plane just got a lot shorter than anyone expected. So what changed?
And now our plan is to take this aircraft and modify it into a hydrogen propulsion flight laboratory.
The December 2025 breakthrough. In December 2025, Rolls-Royce and EasyJet published a report that made aviation executives sit up straight. The findings were straightforward but game-changing. According to their analysis, hydrogen-powered aircraft could handle roughly 80% of all European flights if just 20 major airports installed the necessary hydrogen infrastructure. That's not 100 airports, not 50. 20 hubs like Heathrow, Charles de Gaulle, and Frankfurt could transform the majority of European aviation. What made this report different from earlier projections was the specificity. Previous studies often painted hydrogen as a distant possibility, something that might work decades from now if everything went perfectly. This analysis was built on actual aircraft designs, real fuel cell capabilities, and existing airport layouts. Rolls-Royce and EasyJet weren't speculating. They mapped out flight routes, calculated range requirements, and identified which airports would need hydrogen refueling stations to cover the most traffic. The focus on short to medium-haul flights is critical here. Most European routes fall under 1,500 kilometers. London to Barcelona, Paris to Rome, Berlin to Madrid. These are the bread-and-butter routes for airlines like EasyJet, and they represent a massive portion of total flight volume. Hydrogen aircraft are particularly well-suited for these distances because the technology doesn't need to compete with long-haul jets crossing oceans. It just needs to handle a few hours in the air. The report also highlighted something important about infrastructure timing. Airports take years to build new facilities. If hydrogen refueling stations are going to be ready when the first commercial hydrogen planes enter service in the early 2030s, the planning and construction need to start now. That's why this wasn't just a technical study. It was a roadmap with deadlines, the iron pod moment. Airbus has been talking about hydrogen for years, but talk is cheap in aerospace. What matters is whether you can actually build an engine powerful enough to lift a commercial airliner full of passengers and baggage into the sky. That's where the iron pod comes in. The iron pod is a 1.2 megawatt hydrogen fuel cell propulsion system that Airbus recently tested at full power. That might not sound dramatic, but it represents the first time a hydrogen fuel cell has demonstrated the kind of thrust needed for a real passenger aircraft. This isn't a small drone or a two-seater experimental plane. This is commercial scale power. So what exactly is a fuel cell, and why does it matter? Traditional jet engines burn kerosene. They ignite fuel in a combustion chamber, and the expanding gases create thrust. It's loud, it's hot, and it produces carbon dioxide and water vapor as exhaust. A hydrogen fuel cell works completely differently. It takes hydrogen gas and combines it with oxygen from the air in an electrochemical reaction. The result is electricity, heat, and pure water. No carbon dioxide, no nitrogen oxides, no particulate matter, just water. That electricity then powers electric motors that turn the aircraft's propellers or fans. The entire system is quieter than a jet engine and dramatically cleaner. But the challenge has always been power density. Fuel cells need to be light enough to fly, but powerful enough to move tens of thousands of kilograms through the air at hundreds of kilometers per hour. For years, that balance seemed impossible. The iron pod test proved it's not. Airbus ran the system through the full range of conditions it would face during takeoff, climb, cruise, and landing. The fuel cell held up. It delivered consistent power. It didn't overheat or fail. This was the technical validation that the company needed to move forward with its Zero aircraft program, which aims to put a hydrogen-powered plane into service by the mid-2030s. It's worth understanding what this means in practical terms. Airbus isn't just building a prototype for publicity. They're engineering a propulsion system that will need to pass the same rigorous safety and performance standards as every other commercial aircraft engine. The Iron Pod test was a major step toward proving that hydrogen fuel cells can meet those standards. The contrail problem no one talked about. When most people think about airplane pollution, they picture carbon dioxide. But there's another problem that's been quietly contributing to climate change, and it's literally written across the sky. Contrails. Those white lines that jets leave behind aren't just water vapor. They're ice crystals that form when hot, humid exhaust meets cold air at high altitude. And recent research suggests they might be doing more damage than the CO2 itself. The Blue Condor project in 2025 conducted detailed testing on how different fuels affect contrail formation. What they found was striking. Hydrogen combustion produces water vapor, but it doesn't produce the soot particles and sulfur compounds that traditional jet fuel does. Those particles act as seeds for ice crystal formation. Without them, contrails are far less likely to form, and when they do, they dissipate much faster. Why does this matter? Contrails trap heat in the atmosphere. They act like thin, high-altitude clouds, reflecting some sunlight during the day, but trapping outgoing infrared radiation at night. Over time, this creates a warming effect. Some estimates suggest that contrails and the cloud cover they induce could contribute more to short-term warming than the CO2 emissions from aviation. That's a staggering realization. Hydrogen engines largely eliminate this problem. Because the combustion is so much cleaner, there are fewer particles to nucleate ice crystals. The exhaust is mostly water vapor, which disperses more quickly at altitude. This doesn't mean hydrogen aircraft leave no trace, but the trace they leave is far less persistent and far less warming. The Blue Condor findings added another layer to the case for hydrogen. It's not just about cutting carbon emissions, it's about addressing a form of pollution that's been hiding in plain sight for decades. Airlines and regulators are starting to pay attention because contrails are one of those problems that can't be solved by carbon offsets or efficiency improvements. You either change the fuel or you live with the warming. Why jet fuel's days are numbered. For a while, the aviation industry pinned its hopes on sustainable aviation fuel, or SAF. The idea was appealing. You could produce jet fuel from plants, waste oils, or synthetic processes, and it would burn in existing engines without any modifications. Airlines could decarbonize without redesigning their fleets. But SAF has run into serious problems. First, it's expensive. SAF can cost 2 to 4 times as much as conventional jet fuel, and that price gap hasn't closed as quickly as expected. Second, it's hard to scale. The supply chains for feedstocks like used cooking oil or agricultural waste are limited. There simply isn't enough waste oil in the world to replace all the jet fuel currently being burned. Synthetic SAF, made from captured carbon and hydrogen, is theoretically limitless, but it requires huge amounts of energy and infrastructure that doesn't exist yet. Hydrogen sidesteps many of these issues. Green hydrogen is produced by splitting water into hydrogen and oxygen, using electricity from renewable sources like wind or solar. Water is abundant. Renewable electricity is getting cheaper every year. And unlike SAF, which still relies on complex refining processes, hydrogen production can be scaled up almost anywhere. You don't need oil wells or refineries. You need water, electricity, and electrolyzers. This is why major players are moving fast. Airbus and Rolls-Royce aren't just testing engines, they're signing contracts with airports to build hydrogen production and refueling facilities. These so-called hydrogen hubs would allow airports to generate their own fuel on site, cutting ties with the traditional oil supply chain entirely. That's a fundamental shift in how aviation could operate. Airports like Heathrow and Schiphol are already exploring pilot projects to install electrolyzers and storage tanks. The goal is to have small-scale hydrogen refueling capability in place by the late 2020s, with larger facilities ready by the early 2030s. This isn't speculative anymore. It's infrastructure planning with budgets and timelines. The other advantage is geopolitical. Jet fuel prices are vulnerable to oil market volatility and supply disruptions. Hydrogen produced locally from renewable electricity is far more stable. Countries without oil reserves could produce their own aviation fuel. That's an attractive proposition for energy security. The minus 253 degrees Celsius challenge. Here's the catch. Hydrogen is the lightest element in the universe, which makes it great for efficiency, but terrible for storage. At normal temperatures and pressures, hydrogen is a gas that takes up enormous amounts of space. To store enough hydrogen to power a commercial flight, you need to compress it or cool it down. A lot. Liquid hydrogen is stored at -253 degrees Celsius. That's just 20 degrees above absolute zero. At that temperature, hydrogen becomes a dense liquid that can be stored in manageable volumes. But keeping it that cold requires heavily insulated tanks, and those tanks are heavy and bulky. You can't just put them in the wings like you do with jet fuel. Aircraft wings are the traditional place to store fuel because it's structurally efficient and keeps the weight balanced. Jet fuel sloshes around in the wing cavities without needing separate pressure vessels. Liquid hydrogen can't do that. It needs cylindrical or spherical tanks with multiple layers of insulation to prevent heat from seeping in. If the hydrogen warms up, it expands rapidly and needs to be vented, which wastes fuel and creates safety risks. This means hydrogen aircraft need to store fuel in the fuselage. That's a big design constraint. The fuselage is where passengers, cargo, and systems usually go. Adding large fuel tanks means rethinking the entire layout of the plane. It also changes the aerodynamics. A traditional tube and wing aircraft isn't optimized for carrying heavy, bulky tanks in the body. That's why the blended wing body design has suddenly become the hottest topic in aviation. A blended wing body aircraft looks more like a flying wing than a traditional plane. The fuselage and wings merge into a single, wide, flat shape. This design has more internal volume, which is perfect for hydrogen tanks. It's also more aerodynamically efficient, which helps offset the weight penalty of the insulated tanks. Airbus has been researching blended wing body designs for years, but hydrogen is giving the concept a real reason to exist. If you're going to redesign the entire aircraft anyway to accommodate liquid hydrogen, you might as well optimize the shape for efficiency at the same time. The result could be a plane that looks radically different from anything flying today. There are other engineering challenges too. Hydrogen is a tiny molecule, and it can leak through materials that would easily contain other fuels. Tanks need to be made from special alloys or composites. Seals and valves need to be designed to handle cryogenic temperatures. Refueling procedures need to be safe and fast because airports can't afford long turnaround times. All of this is solvable. Liquid hydrogen has been used in rockets for decades, so the core technology exists. But scaling it up to commercial aviation, where safety standards are even higher and cost pressures are intense, is a massive undertaking. That's why aircraft manufacturers are investing billions into research and testing. They know the clock is ticking. What this actually means for flying.
European plane manufacturer Airbus has unveiled plans to bring hydrogen-powered passenger planes into service by 2035.
So when will you actually be able to book a ticket on a hydrogen plane? The realistic timeline points to the mid-2030s for the first commercial hydrogen aircraft entering service. Airbus has publicly committed to having a hydrogen-powered plane ready by 2035. That's not just a concept, that's a target for certification and delivery to airlines. The first routes will likely be short-haul flights in Europe. Think London to Amsterdam, Paris to Berlin, or Madrid to Lisbon. These routes are heavily trafficked. They fall within the range capabilities of early hydrogen aircraft, and they connect airports that are already planning hydrogen infrastructure. Airlines with strong environmental commitments like EasyJet or KLM are the most likely early adopters. What will passengers notice? Probably not much during the flight itself. Hydrogen fuel cell engines are quieter than traditional jets, so takeoff and landing might be less noisy. The cabin experience should be similar to what you're used to, though the exterior of the plane might look different if it's a blended wing body design. Refueling times could be slightly longer at first, but airports are working to make the process as seamless as conventional fueling. Ticket prices are harder to predict. Initially, hydrogen flights might cost more as airlines recoup the investment in new aircraft and infrastructure. But as production scales in hydrogen becomes cheaper, the cost could come down. Some projections suggest that green hydrogen could eventually be cheaper than jet fuel, especially if carbon taxes make fossil fuels more expensive. Long-haul flights are a different story. Hydrogen works well for short to medium distances, but flying across the Atlantic or Pacific requires much more fuel, and the weight of the tanks becomes prohibitive. For those routes, SAF or hybrid systems might be the solution for a longer period. Hydrogen will dominate regional and continental travel first. Several airlines have already signed letters of intent to purchase hydrogen aircraft once they're available. These aren't binding orders yet, but they signal serious interest. The aviation industry knows that regulators and passengers are demanding cleaner options. Hydrogen offers a path to near-zero emissions without waiting decades for entirely new technologies to be invented. The pieces are falling into place faster than most people realize. Test flights are happening, infrastructure contracts are being signed, aircraft designs are moving from sketches to engineering blueprints. The leap from jet fuel to hydrogen isn't a distant fantasy anymore. It's a transition that's already underway, and the first passengers will be boarding these aircraft within the next 10 to 15 years. Aviation is entering a new era, and it's not just about being greener. It's about rethinking what flight can be.